Hello, my name is Marco Olvera, and today we're going to be reviewing my final project. We're going to be presenting our results about the design of a reactor for sucrose hydrolysis. And this is part of the final project of the signature Reactors engineering. First of all, we need to talk about kinetics and reaction model. Is the sucrose that with water produces glucose and fructose. In this model, we took into account three considerations, such as we work with constant density. This means that we don't work with the expansion factor, such as homogeneous reaction in solution, that we don't take into account any heterogeneous catalysts, sorry. And then I didn't take into account this, but this is important to know that exists, that this reaction can be acid catalyzed, and we can talk about this later. Okay, then the rate equation is equal to the kinetic constant times the concentration of sucrose times the concentration of water. But to make it easier and work with an easier rate equation, we need to have water in excess in order to make so the first order rate equation. As making water in excess, the concentration of water remains practically the same. So we have now a new kinetic constant that is K prime equals to K times the concentration of water. And then this rate equation changes into K prime times the concentration of sucrose. K prime depends strictly of the temperature as Arrhenius using Arrhenius equation that K prime as a function of temperature is equal to the pre-exponential factor times E to the minus activation energy over RT. Okay, so the process overview, I found several articles that talked about the solution preparation that usually you need to use about a 0.58 molar concentration of sucrose, but in this project I used a 1.5 molar concentration that was changed in order to see how affected to the costs, but we're gonna talk about that later. Okay, the calibration, the solution needs to be heated to 30 up to 60.5 degrees. And in my model, I used that it started at 25 because I found some of the enthalpies and mostly enthalpies because the CPs were in function of the temperature as well. And then the inversion models, or I mean, inversion methods that these are acid catalyzed, as I mentioned before, can be using hydrochloric acid or any other acids, such as and enzymatic catalysts as well. Okay, then how needs to be stored? Well, we need to store it in clean, sealed containers at room temperature, and we need to protect the products from light because they are photosensible. Then, talking about equilibrium, it needs to be settled for at least 1 week in order to digest and have the final kinetic values as we see in analytical chemistry. And then finally, talking about the waste, we need to dilute acidic sugar waste stream if we work with a an acid catalyst, and then neutralize it with a weak base if possible. Okay, talking about the first configuration, a single CSTR, the parameters I used was the initial concentration as a 1.5 molar. The target production was the biggest amount, that is 1800 kilograms per day, and the target conversion is 0.88. And then the operation temperature is about 80 degrees Celsius, but in the next slide we're going to see that this was because it was the better operating temperature, as we can see in the next slide. Well, and the design results were that the residence time is about 2.2 days. The flow rate that is about 0.077 liters per second, and the required volume is about 14.5 cubic meters. And this was what I was talking about. The operation temperature. If the operating temperature increases, then the residence time decreases. If the residence time is bigger, then the volume also is going to be bigger. So we need to have the smallest residence time possible in order to have the smallest volume possible. So this is why we use that the operating temperature is about 80 degrees Celsius. Okay, for the next configuration, we're gonna see that we use the CSTR and the PFR in series. This needs to achieve the minimum volumes throughout combined reactor stages in order to make also the most affordable configuration. Then I did a Levin spill analysis that is the 1 over the rate equation in the y-axis, and then the conversion in the x-axis. The first stage is about CSTR handles the initial height rate phase up to x1 0.5. This value is arbitrary and it could be settled to more, but I figured it out at the end of the calculations, but it could be changed, and the change would lead into a better process. And then the second stage is a PFR. As we see in this graph, we can manipulate it up to 0.5 as a CSTR, as we know that the CSTR is a normal rectangle, and a PFR as this um, as this graph increases, then we can use a PFR as it is the area behind the curve. So this makes a better and an optimal process having the CSTR and before the PFR. Then we need we obtained that the conversion of the CSTR was about the volume of the CSTR was about 1.97 cubic meters, and then the PFR from 0.5 conversion to a 0.88 was about 2.82 cubic meters, and this gives a total volume of about 4.8 cubic meters. That this is really interesting because it's a 67 reduced volume, comparing it to just a CSTR. Okay, the reactor performance analysis. This is really interesting because I plotted for the PFR several graphs. The first of the three is the conversion versus the reactor volume. And as we can see, it starts in 0.5, that is the exit of the CSTR, and as the conversion increases, the volume also increases. Then the concentration profile, it is logic and to have less concentration as the because it is reacting as we saw in the first graph. And then the temperature evolution. This is the temperature profile that this is also really interesting because we can see the difference in between the inlet and the outlet temperatures. That this means that the temperature is changing all through the process of the PFR as we consider it adiabatic, and we see that this increases as the volume also increases. Okay, for the economic evaluation, we have that the daily costs of the raw materials of basically the sucrose, 54,409 per day, dollars per day, and the utilities are 3.45 per kilowatt. And the total energy usage that this is from our energy balance is about of 1.72 kilowatts. So we have a capital expenditure of about 7.94 million. This is really a lot because in the volume reference we got that it was about 3.1 million, but as we work in this configuration that for me and the given results, it's the better one, considering that doesn't need a lot of volume involved or a lot of uh, residence time. And it this makes the process a little bit expensive in comparison to the reference values of the expander. And also, like the values of concentration or the conversion, these values were arbitrarily chosen, just like a mean of the intervals given. Just like n equals 0.6 was the mean of the interval that it was from 0.5 up to 0.7. And the cost reference was 3.1 million, as I mentioned before. And then about talking about the discussion and evaluation, first of all, the sensitivity. The system is highly sensitive to temperature. Increasing temperature from 50 to 80 reduces residence time by 30 times. Then the optimal setup, CSTR and PFR in series, is the most suitable, as I said, minimizing capital investment while maintaining production rates. For future work, we can evaluate any catalysts with some other conditions considered, just like having our because in my balances I didn't use the difference in the CPs, but this must be used in order to get a robuster analysis. And then for the economy, final conversion percentage is the most expensive design component because in order to get our conversion needs to increase the volume 0 liters or cubic meters. Finally, these are the reference I used in my final project.